Hi, this is the second video for Chapter 12. In this one, we're going to talk about contingency tables and doing hypothesis tests for independence. So here are the requirements. We have to have randomly selected sample data, and the sample data are going to be represented in a table that has rows and columns. That's what we call a contingency table. And one of the requirements for doing a test of independence is that the expected frequency in each cell in the table has to be at least 5. And again, just like with the goodness of fit test, it doesn't matter what the observed frequencies are, just what the expected frequencies are. Our null and alternative hypotheses for this kind of test are always going to be the same. The null hypothesis will always be that the row and column variables are independent, and the alternative will be that the row and column variables are dependent. Again, for this type of test, we're using the chi-square distribution to find our critical values, and the degrees of freedom are going to be r minus 1 times c minus 1, where r is the number of rows and c is the number of columns. And this type of test is always right-tailed. One thing to be careful of is that finding a relationship between the row and column variables doesn't mean that there's a direct cause and effect link between the two. It just means that there's a relationship. Here's our test statistic. This looks just like the one that we had for the goodness of fit test. So we still have O being the observed frequency, and E the expected frequency, and we still find the test statistic the same way with the same formula. The expected frequency is calculated a little bit differently than it was for the goodness of fit test. So to find your expected frequency, you have to take the row total times the column total for whatever row and column your value is in, and then divide that by the grand total for the whole table. Here's an example. Common colds are typically caused by a rhinovirus, and in a test of the effectiveness of echinacea, some test subjects were treated with echinacea extracted with 20% ethanol, some were treated with echinacea extracted with 60% ethanol, and others were given a placebo. All of the test subjects were exposed to rhinovirus. The results from this are summarized in the table that you'll see in the next slide. And we're going to use a 0.05 significance level to test the claim that getting an infection, a cold, is independent of the treatment group. So here's the table with our results. We can see that with the placebo, that 88 were infected and 15 were not. With the 20% extract echinacea, 48 were infected and 4 were not. And with the 60% extract of echinacea, 42 were infected and 10 were not. So the question is whether the difference in the treatment really made any difference as to how many people got infected with the cold and how many didn't. We have here just an example of how you would find the expected frequency if you had to do it by hand. So for example, if we're trying to find the expected frequency for the very first cell, where our observed frequency is 88, so this cell right here, then we would look at the total for the first row and the total for the first column. The total for that first row going across this way is 178. The total for the first column, the 88 plus the 15, is 103, and the total for the whole table is 207. If we apply the formula, we get 88.57. So that's the value we would expect to see for this cell. And again, what we're looking at for our test statistic is the difference between the observed frequencies and the expected frequencies. If they're far apart for the most part, then our test statistic is going to be large and our p-value is going to be small. If they're not far apart, then our test statistic will be small. Now, if we're going to do this hypothesis test, we have to check that the requirements are satisfied. So we had a random sample, and if we look at our expected frequencies for the different cells, they're all at least 5. And here's our null and our alternative hypothesis. Our null hypothesis is that the row and the column variables are independent, and those were whether or not the person was infected and what treatment group they were in. Our null hypothesis is that getting an infection is independent of the treatment. And our alternative hypothesis is that getting an infection is not independent of the treatment. Those two are related. And again, we're going to look at using StatCrunch to find our test statistics and critical values. So what we would do with StatCrunch is we would just type in the values from our table, and I go ahead and label these so that I know what I'm looking at. And you also have to put your row labels in another column. So in this case, I put them in that last column. Then what we do with this is we select Stat, Tables, Contingency, and with summary, since we're just using summary data. In other words, it's already in a table for us. And then we select what the columns are for our table. So we want the placebo, the echinacea 20%, and the echinacea 60%. Those are the columns. And then our row labels we put in that last column, which was just called variable 5. So once we do that, we can click on next, and you'll see a window that looks like this. And when it brings up your contingency table, you can have it show any of these various things. So the row percentages, the column percentages, the percent of total for each one, or the expected frequencies for each cell. In this case, I didn't check any of these, so all it's giving us is just the contingency table. Here's our contingency table. And notice it does give you totals for rows and columns. And we've got a chi-square test statistic. Our degrees of freedom is 2, because remember that's the number of rows minus 1 times the number of columns minus 1. Since we had 2 rows and 3 columns, that gives us 1 times 2. So it's 2 degrees of freedom. The value of our test statistic turns out to be 2.925. And that gives us a p-value of 0.2316. Since we were testing with a significance level of 0.05, our p-value is larger than that, so our conclusion would be that we would fail to reject the null hypothesis. And again, just like we did for the goodness of fit, we could find our critical value using StatCrunch if we wanted to. We would just put in 0.05 for our probability and use 2 for our degrees of freedom. And this would be our critical value. So here's the comparison with our critical value, the 5.991, with our test statistic, which was 2.925. That shows that our test statistic is not in the rejection region. So we're not going to reject our null hypothesis of independence. And what that means is it looks like getting an infection is not related to the treatment group, which suggests that echinacea is not making a significant difference in whether a person gets infected with a cold or not. So here's the big picture with tests of independence. Again, we're comparing the observed frequencies to the expected frequencies. If these two are close for the most part, then we end up with a small chi-squared value, a small test statistic, and a large p-value, which is what we saw in that last example. And in that case, our conclusion is that we fail to reject independence. If the observed and expected frequencies are far apart, then we end up with a large test statistic and a small p-value. And in that case, we would reject independence, which means there's evidence to show that the two variables are related. Now we're going to look at another example, and this has to do with treatment for headaches, and we're going to put these values into StatCrunch and see what we come up with. So here are the values from the table that I just typed into StatCrunch. This time I put my row labels in this first column. So now we want to do our hypothesis test, and to do a hypothesis test with a contingency table, we do stat tables, then contingency, and again we're doing this with summary data. So the columns for our table are going to be drug and placebo. Our row labels are in the first column, which is just named var1. And if you want to, you can put in a label for your column variable here. So let's just call this treatment. And this time let's also have it put in the expected frequencies. Then we click on calculate, and here are our results. Notice that in each one of these cells now it has the expected frequency, so we can do a little bit of comparison between the observed frequencies and the expected frequencies. In this case, our degrees of freedom was only 1 because we had 2 rows and 2 columns. So our degrees of freedom ends up being 1 times 1. And our test statistic is only 1.798. That gives us a p-value of 0.1799. And if we want to find our critical value, then we use our chi-squared calculator. Our degrees of freedom here is only 1, and if we're using a 0.05 significance level, we put the 0.05 in there, and then again we have to change this to a greater than or equal to since it's a right-tailed test. Now this picture looks a little bit funny. That's because our degrees of freedom is only 1. So this is a very flat picture, but it did give us our critical value of 3.84. So we can compare that to our test statistic of 1.798, and that would mean our test statistic is over here, not in the rejection region, because the rejection region starts right here at 3.84 and goes out to the right. So whether we look at our critical value compared to our test statistic or our alpha significance level compared to our p-value, either way, our conclusion is going to be that we fail to reject the null hypothesis, which means again that in this case the drug doesn't seem to be effective in a treatment for headaches because the reaction and the treatment seem to be independent. One more example. In this one we have a contingency table that compares employment status and the responses to a specific survey question of yes, no, or undecided. So in this one, again, if we just type these values into StatCrunch, run our contingency table hypothesis test, then we have 2 degrees of freedom because we had 2 rows and 3 columns. That means we're taking 1 times 2, so that's 2 degrees of freedom. Our test statistic is going to be 5.94. That gives us a p-value of 0.0513. If we're testing at the 0.10 significance level, then our p-value is smaller than alpha, and that means our conclusion would be to reject the null hypothesis. And that means we have enough evidence to say that the employment status and the answers to the survey question are related, that they're not independent.